let's jump into 4 examples related to thermal energy and kind of changes in matter. So there's going to be a couple of examples related to specific heat capacity and then latent capacity as well. All right, so let's take a look. So aluminum, it provides us the specific heat capacity for aluminum per kilogram degrees Celsius of an unknown mass, so we don't know what the mass is, has been placed in 750 milliliters of water. And we have the specific heat capacity there. The water was originally at a temperature of 16 degrees Celsius, and the aluminum piece was at a temperature of 87. So after some time elapsed, okay, the mixture settled at a temperature of 17.8 Celsius. So it looks like the aluminum itself was cooling, okay, and then the water, okay, was heating up, okay, ever so slightly, really just by a degree and a little bit there. Okay, so one is losing kind of heat and the other one is gaining heat. So what is the mass of the aluminum under this experiment? And we can assume that 1 milliliter is equal to 1 gram. Okay, so well, let's write down all the given pieces of information here. So I'm gonna kind of get started and then just hopefully let you know what's happening. So first of all, you know, if you take a look at this, so it's almost like, okay, we have something like this where we have some kind of water, maybe in some container. All right, so here it is. All right, then we put some piece of aluminum inside. So as we kind of drop this in there, all right, so this aluminum piece kind of gets placed in there. And what's going to happen is, as the aluminum piece is at a higher temperature, the temperature falls down. So that means there's a heat transfer that we're going to be experiencing here. All right, so that's the aluminum piece and then the water. And then we have the following. So aluminum, so we have the specific heat capacity of aluminum. I'll just put A, and that's 898 and joules per kilogram degrees Celsius. We have a 750, so that's going to be the mass. I know that it's volume, but notice that it is telling us that we have 1 milliliter is equal to 1 gram. And so this is the mass of the water. So I'm going to put H2O is equal to, and this was aluminum, sorry, and this was H2O, and that's 750 grams approximately, which equals to, I guess, 0.75 kilograms, okay, if you wanted to change that and make it still standard. The water itself, so the specific heat capacity of water is 4184, and that's going to be joules per kilogram degrees Celsius. Now the water original temperature, so notice that we're going to have a change of temperature for water. So change of temperature, this is going to be for the water, and that's going to, it's going to end up at 17.8. right? And it starts off at 16. So this is nothing else but just 1.8 there. That's all that it is, okay, in terms of a change in degrees Celsius. Now the change for the aluminum, okay, so that's for the aluminum. So it was originally at 87, and then the final was 17.8, so minus 87 there. Okay, so let's pop that in the calculator and see what that gives me. So this is minus 69.2 degrees Celsius. Okay, so just because of the change in temperature, one is losing and then one is going to be gaining. All right, so it's going to get transferred from one to the other and then it's going to settle off. All right, so that's what we will have. What is the mass of the aluminum under this experiment? Okay, so we're going to have, okay, so the change, okay, in water, right, in terms of the magnitude is going to be the same as, maybe I'll put it in a different color, as the change in the aluminum. All right, so now, because we know everything with the water, so we can kind of go ahead and do that first. So the change in water that you have, this is equal to the mass, the specific heat capacity, and then the delta T. So let's substitute all that in. So 0.75, this is 4184, so the units are all aligned there. And then the change is 1.8, so it's not very much, Okay, so this is what we have there. So 0.75 times 4184 times 1.8, which is 5648 and 0.4 joules. All right, so that's how much energy this has gained, right, because of the temperature increase there that we can see. Now the aluminum, on the other hand, is going to lose that energy, right? So for aluminum, so if I'm going to take this thing, I'll just put it right below it. So it's going to be losing that much energy. So therefore, so this is going to be negative 5648.4 joules, right? So because it was at a higher temperature, so now it's going to be falling through. And this is equal to, so this is mc delta T, but of course this is all for aluminum. So let's plug in all the numbers. Now we don't know what the mass is, that's what we're trying to find. The specific heat capacity for aluminum is 898. 898, that's what they give us, and then the change was 69.2. All right, and then of course this right here. So we just have to be careful with the negatives, although the two negatives are going to cancel, right? So we're going to have a negative negative, so we can get the mass, and obviously mass should be positive overall. So now it's just a matter of taking, so our mass is equal to, and now I can replicate this whole thing. So duplicate that, and this is going to be divided by, I'm going to take this, so I'll steal this away from here so I don't have to rewrite it again. So this is going to get divided on both sides. All right, so now let's plug it in so that we can find out how much mass we had. The negatives cancel, so I'm not going to put that in there. 48.4 divided by 898, and so that's divided by that, and then divided by 69.2. I should have just put it in brackets. I wouldn't have to do that. So this equals right there the mass, which is 0.09, 0.89, etc. So within there, I don't think that it stated what was the mass. It didn't tell us in grams or kilograms. So if we're going to keep it in kilograms, which is this, the significant figures, I guess, from just by looking at these, so 2 sig figs overall, that would have been the mass. If you want to keep it in grams, it would have been 91 grams. All right, so there you have it. So that's for this example. It's a nice example because it's a transfer of energy from one to the other. So that is it for this one. Now this second example that we have in here, so it says, you can repeat this. However, we're going to be swapping aluminum for gold. All right, so we can assume, that now instead of aluminum, we have gold. So this is going to be a little bit easier for us. So I'm not going to redo the entire calculations. So you can go back to that previous example if you like. But I am going to start, obviously, with the water. And the only change for me is gold has a different specific heat capacity. So that's what we're going to do. So I'm not going to recalculate this. So if everything stays the same, so if this is what I have, so I'm going to just copy this out. All right, and I'm going to paste it in here. So that was for the water. Now, in terms of all of the other pieces of information that were provided to us, so in terms of the gold, so we have the specific heat capacity of gold, and that is, so notice it's 0.129. This is per gram. All right, so we have to be careful, although, I guess I can keep it in grams for now. I can change it to kilograms later. So this is joules per gram for every change in temperature. Just because it says Kelvin, it doesn't matter. So a change in Kelvin is the same thing as change in degrees Celsius. So that is not a big deal. I'm going to actually just kind of remove this out so that, you can certainly swap it whenever you see that. All right, so now let's try it out. So what we have is we need all of this. So that's going to be my change. And this is going to be negative, right? So in terms of gold. And this is going to be equal to the mass times the specific heat capacity times this. Now the change in temperature from the previous was 69.2. All right, so mass times 0.129 negative 69.2. Now please keep in mind I'm leaving this in grams, so our answer is going to be in grams instead of kilograms. And this is going to be minus 5648.4 joules. So now the mass of gold is, once again, so that's going to be all of this that we have in here. Now you're going to take that and you're going to divide it by all of this. So you're going to have that. So duplicate it, put it right back in there. And let's take a look and see what we're going to get if we punch this into the calculator. So 5648.4 divided by 0.129 multiplied by 69.2. I got rid of the negatives there. And notice this is 632.7, but this is grams, right? So two significant figures. This is approximately 630 grams, or 0.63 kilograms. All right, so that's it for this one. This example is with latent heat. So that means you're not increasing any temperatures. This is the change in state. So notice it says fusion there. So the latent heat of an unknown substance during fusion. And notice how enormous that is. Now, please recall, so the heat, this is just simply mass, okay, times the actual latent heat capacity in there. So we have no changes in temperature, right? So it's just the energy which is basically being taken away from the bonds, okay, so that it can change state, so either going up or going down. So within here, so how much heat would it take to melt 468 grams of the unknown substance? Okay, so that's a question that they ask us. All right, well, this one is actually per kilogram, so let's change this to kilograms. So 0.468, that's in kilograms, times, and then all you have to do is just take the latent capacity, okay, that we have in here, 10 to the 6. And that's all that we're going to do. So let's calculate it and find out what this will give us. So 0.468 times and 6.876, so times 10 to the 6. Okay, so let's hit that in there. And that's quite a bit, okay, of energy. So 968, this would have been joules. So we have, what, three significant figures. I'll put this in scientific notation. So 1.81 times 10, and it's what, 1, 2, 3, 4, 5, 6. All right, joules. So that's how much energy you would need, okay, for this particular item. So with respect to melting. Okay, so that is it for this example. Okay, so welcome to the last example. This one is going to be the combination. Okay, so as you have kind of your specific heat capacity and the latent capacities. Okay, so we have liquid water, all right, which is 4.184 joules for every gram per Celsius. That indeed is true. That's what a little calorie is. And then the specific latent heat of vaporization. So basically going in from a liquid to a gas. Notice how much bigger that is. Okay, it's enormous in comparison just to changing temperatures. So breaking those bonds, so going from a liquid to a gas, takes quite a bit of energy. It's a lot of potential in there. So how much energy would have to be transferred if 125 milliliters of water, currently at 21 degrees Celsius, was to vaporize entirely? Okay, and we'll assume that 1 gram is approximately 1 milliliter. Okay, so this is basically two things happening in here. So two kind of states. So what happens is, so initially, so we're starting off at 21 degrees Celsius, right? So that's our initial temperature. And now this temperature is going to keep on increasing, right? So it just keeps going up, going up. Obviously, it's going to, so assume that it's about 100 degrees Celsius. And then during this step, it's going to take a certain amount of energy in here, okay, so that all of this, okay, starts to, okay, take off and become basically a gas and vaporize in there. So this is going to be kind of going out, right, and then releasing it. Now we want to get rid of all of it. So this is kind of a two-step process. So step number one, we have in terms of the specific heat capacity, and this is step number two in terms of the specific latent heat, okay, and this is a vaporization. So let's do first step number one. So we need Q is equal to mass times specific heat capacity times the change in temperature. All right, so the mass, we had 125 milliliters, okay, which is the same thing, okay, as 125 grams. Now, notice that this, okay, is per gram, right? So specific heat capacity is per gram. So I'm not going to actually change this to kilograms. So I'll leave it at 125 grams multiplied by, this is going to be 4.184 joules per every gram for degrees Celsius. So notice the grams cancel. And then this is multiplied by the change in temperature. So that change in temperature is from 100, okay, goes to 100 from 21, and that's going to be 79 degrees Celsius, right? So 79 degrees Celsius. So the Celsius cancels out and that's gone. So all you're going to have left is just the joules, right? Which is what we want. So now let's punch that into our calculator and see what it gives us. So 125 times 4.184 times 79. So 41317 joules. And this is just to get the temperature up, right? To kind of the boiling point for this. Now, for step number two, right? So for this one, the heat is related to the mass times the latent heat, okay? So in this case, so we're assuming that it's 125 grams. Now they give us, let's take a look. Okay, they give it to us still per gram, so that's fine. So I'll just leave it as it is. So this is going to be multiplied by, and then that is 2230. So 2230. So this is grams, okay, and this is joules per gram. So that will cancel. And then let's see what this will be. 125 times, it's obviously going to be way more. And indeed, that's the case. So 278750 joules. Now you have to add these two together. So if you're going to be adding these two together, so this one and this one, okay, so that's going to be Q1 plus Q2. So those are from the two steps. So I already have this on the calculator. I'll add the other one, which is 41317. And that's going to be 320067 joules. And there you have it. Now, if we want to round, let's see what was the minimum one. I guess two significant figures. You can round to whatever you like, but I guess if you keep it to 2, so you have that answer. All right, and that would have been that example. It's a nice example because it's a combination, okay, with changes of state of matter in here. All right, so that is it. Thanks for watching. See you in future videos. Bye, everybody.